The origins, spectral interpretation, resource identification, security, regolith explorer, commonly known as OSIRIS-REx, represents a pinnacle of modern planetary science and engineering. To understand the gravity of this mission, we must first situate ourselves within the broader context of solar system exploration. For decades, humanity has gazed upward, relying on remote sensing, telescopes and flyby probes, to decipher the composition of the celestial bodies that share our orbit around the Sun. We have collected meteorites that have fallen to Earth, surviving the violent heat of re-entry, but these samples are inherently compromised, altered by our atmosphere and contaminated by the terrestrial environment upon impact. The OSIRIS-REx mission was conceived to bridge this gap, to travel into the void, touch the face of an ancient relic, and bring a pristine, unaltered piece of the early solar system back to our laboratories. The selection of the target was a process of rigorous elimination. From the over 500,000 known asteroids at the time of mission planning, the team needed a candidate that was accessible, carbon-rich, and of a specific size to ensure a stable rotation. That candidate was 101,955 Bennu. The mission profile was ambitious, requiring a journey of billions of kilometers, a delicate orbital insertion around a microgravity body, a perilous touch-and-go sampling maneuver, and a precise return trajectory to Earth. The spacecraft itself was a marvel of instrumentation, equipped with the OCAM's camera suite, the OTS thermal emission spectrometer, the OSIRIS visible and infrared spectrometer, the OLA laser altimeter, and the REx X-ray imaging spectrometer. These instruments were designed not just to map the asteroid, but to understand its chemical abundance, its thermal properties, and its mineralogy before a physical sample was ever attempted. When OSIRIS-REx launched aboard an Atlas V rocket, it began a 7-year journey that would rewrite our understanding of the formation of the solar system. The spacecraft did not fly directly to Bennu. Rather, it performed a complex celestial dance, utilizing Earth's gravity in a slingshot maneuver to align its inclination with that of the asteroid. This phase of the mission, the cruise phase, was a period of quiet anticipation, punctuated by instrument calibrations and trajectory correction maneuvers, ensuring that when the spacecraft finally arrived at its destination, it would be perfectly positioned to begin its detailed survey. We turn our attention now to the object of this pursuit, asteroid Bennu. To the uninitiated, Bennu might appear as merely a rough, diamond-shaped rock tumbling through the vacuum. To the planetary scientist, however, Bennu is a B-type asteroid, a subcategory of carbonaceous asteroids that are primitive and dark. It is a time capsule. Bennu is a near-Earth object, or NEO, with an orbit that intersects Earth's path, making it potentially hazardous in the distant future. Its shape is that of a spinning top, with a pronounced equatorial ridge, a morphology common among asteroids that rotate rapidly. This shape suggests that over millions of years, the weak gravitational holding of the asteroid has allowed material to migrate toward the equator due to centrifugal force. Bennu is not a solid monolith. It is what astronomers classify as a rubble pile. It is an amalgamation of rocks, boulders, and gravel, held together not by chemical bonds or the strength of solid stone, but by the tenuous grasp of its own microgravity and van der Waals forces. It is essentially a floating mountain of debris, roughly 500 meters in diameter. Its surface is incredibly dark, reflecting only about 4% of the sunlight that hits it, making it darker than fresh asphalt. This low albedo indicates a surface rich in carbon, the fundamental building block of life as we know it. The thermal inertia of Bennu, how quickly it heats up in sunlight and cools down in darkness, tells us about the porosity and texture of the surface material. Before arrival, models suggested a surface that might be somewhat smooth, covered in fine-grained regolith similar to sand. This hypothesis was based on thermal data and comparisons with other bodies. However, the reality of Bennu would prove to be drastically different and infinitely more complex. As OSIRIS-REx approached Bennu, the high-resolution imagery began to reveal a landscape that defied the pre-mission models. The team had designed the sampling mechanism to ingest particles up to 2 centimeters in size, anticipating vast beaches of fine sand where the spacecraft could safely descend. Instead, what the cameras revealed was a rugged, hostile world. Bennu was strewn with massive boulders, some the size of buildings, creating a chaotic terrain with very few hazard-free zones. The surface was geologically diverse, with bright boulders of pyrozene originating from the asteroid Vesta, indicating a history of interplanetary collisions, sitting atop the dark, indigenous carbonaceous material. This unexpected ruggedness presented a critical engineering challenge. The original mission parameters called for a landing site with a radius of 50 meters, a clear circle where the spacecraft could touch down without risk of striking a boulder with its solar arrays. The reality of Bennu's surface meant that no such site existed. The team was forced to shrink their target requirement significantly. They had to identify a site that was mere meters across, surrounded by towering hazards. This required a fundamental update to the spacecraft's navigation logic. The team implemented a system known as natural feature tracking. Instead of relying solely on radar altimetry, the spacecraft would take real-time images of the surface during its descent, comparing them to an onboard catalog of known surface features, craters, rocks, and ridges. By triangulating its position relative to these landmarks, OSIRIS-REx could autonomously adjust its path to ensure it landed in the safety zone. After a meticulous search, 4 candidate sites were identified and named after birds: nightingale, kingfisher, osprey, and sandpiper. Nightingale, located in a high-latitude crater in the northern hemisphere, was selected as the primary site. It offered the best access to fine-grained material, which was essential for the sampling mechanism, but it was also surrounded by massive obstacles, including a rock nicknamed Mount Doom. The margin for error was almost non-existent. The spacecraft would have to descend into this crater, avoiding the walls and the looming boulders, to tap the surface of a rotating body millions of kilometers from Earth. The climax of the orbital phase was the touch-and-go maneuver. This was not a landing in the traditional sense, where a probe settles on the surface. Rather, it was a momentary interaction. The mechanism employed was the touch-and-go sample acquisition mechanism, or TAGSAM. This device consisted of an articulated robotic arm with a circular sampler head at the end. The plan was to extend the arm, maneuver the spacecraft down to the surface, and press the head against the regolith. Upon contact, a bottle of high-pressure nitrogen gas would fire, blasting the surface material. This agitation would fluidize the regolith, causing rocks and dust to be blown upward into the collection chamber within the TAGSAM head. On October 20, 2020, OSIRIS-REx began its descent. The sequence was automated, a nervous wait for the mission control team on Earth due to the time delay in communications. As the spacecraft contacted the surface at the Nightingale site, something remarkable happened. The surface of Bennu offered almost no resistance. Later analysis and simulations would reveal that the surface of the asteroid behaved less like solid ground and more like a plastic ball pit or a fluid. If the spacecraft had not fired its back-away thrusters, it might have sunk significantly deeper into the asteroid's interior. The density of the rubble pile was so low, and the cohesion between particles so weak, that the tagsum head plunged roughly half a meter into the regolith within seconds. The nitrogen gas fired as planned, churning up the subsurface material. The camera footage from the event showed a chaotic explosion of rocks and dust. The maneuver was so successful that it actually created a problem. The collection chamber was designed to hold a specific volume of material, but the soft surface and the successful gas blast had driven so much rock into the head that the mylar flap, designed to seal the container, was jammed open by larger rocks. As OSIRIS-REx backed away from Bennu, particles were seen drifting out of the sampler head into space. The mission had collected too much. The team had to rush to stow the sample head into the return capsule to prevent further loss of mass. This was a tense operation, bypassing the usual measurement spins to ensure the precious cargo was sealed safely inside the sample return capsule. With the sample secured, the mission shifted to the return phase. OSIRIS-REx had to wait for the orbital mechanics of the solar system to align once more. In May 2021, the spacecraft fired its main engines to leave the vicinity of Bennu and begin the long cruise back to Earth. This return journey was a mirror of the outbound trip, a quiet coast through the inner solar system, monitored by the Deep Space Network. The precision required for the return was exacting. The spacecraft had to release the sample return capsule at a specific angle and velocity to ensure it would enter the Earth's atmosphere above the Utah test and training range. If the angle was too shallow, the capsule would skip off the atmosphere like a stone on a pond. Too steep, and it would burn up or crush the samples with excessive G-forces. On September 24, 2023, the capsule separated from the main spacecraft. While the OSIRIS-REx mothership fired its thrusters to divert past Earth and continue on a new mission, the capsule hit the upper atmosphere. It became a fireball, streaking across the western United States. The drogue parachute deployed to stabilize the descent, followed by the main parachute. In a moment of relief and triumph, the capsule touched down softly on the desert floor of Utah. Recovery teams, practicing for years, swooped in with helicopters to secure the site. They checked for unexploded ordnance and toxic gases before bagging the capsule and transporting it to a temporary clean room. The sample was safe. The journey of the sample did not end in the desert. It was flown to the Johnson Space Center in Houston, Texas, where a specialized facility had been built to house it. The curation of extraterrestrial samples requires a level of cleanliness that exceeds surgical standards. The samples were housed within glove boxes purged with pure nitrogen to prevent any reaction with Earth's oxygen or moisture. The scientists were looking for organic molecules and hydrated minerals, and any exposure to the terrestrial atmosphere could compromise the data. However, a new hurdle emerged. When the curation team attempted to open the main tagsum head to access the bulk of the sample, they found that 2 of the 35 fasteners holding the lid closed were stuck. The approved tools for use inside the glove box were insufficient to remove them, and the team could not simply bring in standard industrial tools due to the strict contamination control protocols. For months, the team had to work around the stuck lid, accessing only the overflow material that was accessible from the outside of the head or through the mylar flaps. This overflow alone amounted to 70 grams, exceeding the mission's minimum requirement of 60 grams, but the main treasure remained locked inside. It took the design and fabrication of new, specific tools made from surgical-grade stainless steel to finally torque the stuck fasteners free in early 2024. Once the full sample was accessible, the scientific analysis began in earnest. The visual inspection alone was revelatory. The material was incredibly dark, confirming the high carbon content. But as the grains were subjected to electron microscopes, mass spectrometers, and X-ray diffraction, a complex chemical story began to unfold. One of the first major findings involved presolar grains. These are microscopic specks of stardust that predate the formation of our solar system. They are the remnants of ancient stars, red giants and supernova, that lived and died billions of years ago. These grains survived the chaotic collapse of the molecular cloud that formed our sun, and were incorporated into the matrix of asteroids like Bennu. Their isotopic signatures provide a direct link to the distinct stellar environments that synthesize the heavy elements comprising our world. The analysis confirmed that Bennu is rich in carbon and water. The water is not in liquid form, but locked within the crystal structure of clay minerals. This supports the theory that asteroids like Bennu may have delivered the vital ingredients for life, water and organic compounds, to the early Earth. But the findings went deeper. The team discovered a variety of organic molecules, including polycyclic aromatic hydrocarbons and amino acids. These are the building blocks of proteins, the fundamental machinery of biology. Finding them in such abundance on a pristine asteroid strengthens the hypothesis of lithopanspermia, or the delivery of probiotic chemicals via impactors. Perhaps the most shocking discovery, and the one that puzzled scientists initially, was the presence of a crust of bright, salt-like particles on some of the dark rocks. Chemical analysis identified this substance as magnesium sodium phosphate. This was unexpected. While phosphates are known in meteorites, this specific water-soluble form is rare in the geological record of asteroids. On Earth, we find magnesium sodium phosphate in biological contexts or specific evaporating bodies of water. Its presence on Bennu suggests a history of significant fluid alteration. This discovery invites us to reconstruct the history of Bennu. We must understand that Bennu was not always a small rubble pile. It is a fragment of a much larger parent body, likely a planetoid that existed in the early solar system. This parent body would have been large enough to retain heat, perhaps from the decay of radioactive isotopes like aluminum-26. This heat would have melted the ice within the rock, creating vast internal oceans or hydrothermal systems. The fluid would have circulated through the rock, altering the minerals, depositing veins of carbonates, and concentrating elements like sodium and phosphorus. The presence of magnesium sodium phosphate strongly implies that Bennu's parent body was an ocean world, possibly similar to the icy moon Enceladus orbiting Saturn today. In this ancient, dark ocean, hidden beneath a thick crust of rock and ice, the water was alkaline and rich in dissolved chemicals. The finding of bioessential sugars and gum-like organic compounds further paints a picture of a complex probiotic chemistry occurring on this parent body. Eventually, a catastrophic collision shattered this world, sending fragments tumbling into the void. Some of these fragments reaccumulated under gravity to form the rubble pile we know as Bennu, preserving the chemical fingerprints of that lost ocean world. The implications of these findings are profound. They suggest that the conditions for life, liquid water, organic carbon, and essential elements like phosphorus, may be widespread in the outer solar system and within the asteroid belt. The strange substance found on Bennu is a witness to a wet, dynamic past that occurred 4.5 billion years ago. It tells us that the early solar system was a place of chemical evolution, where the ingredients for life were being cooked up in the interiors of planetoids long before Earth had cooled enough to support oceans. While the samples from Bennu will occupy scientists for generations, the spacecraft that delivered them has not finished its work. Following the release of the sample capsule, the spacecraft was rebranded as OSIRIS-REx, short for OSIRIS-Apophis Explorer. Its new target is the asteroid 99942 Apophis. Apophis is an S-type asteroid, distinct from the carbonaceous Bennu, consisting mainly of silicate rocks and nickel iron. It is famous for its upcoming close approach to Earth. In 2029, Apophis will pass within 32,000 kilometers of our planet, closer than our geostationary satellites. OSIRIS-REx will enter orbit around Apophis shortly after this close encounter. The mission aims to study how the gravitational tidal forces of Earth affect the asteroid. Will the close pass trigger landslides? Will it alter the spin state of the asteroid? Will it expose fresh material from beneath the surface? The spacecraft will descend close to the surface of Apophis, firing its thrusters to blast the regolith just as it did at Bennu, although this time without a sampling head to collect the material. This will allow instruments to analyze the subsurface composition and strength. The legacy of the OSIRIS-REx mission is dual-faceted. On one hand, we have the physical samples, the canister of black dust and rock that holds the secrets of our cosmic origins. These grains of sand are currently being distributed to laboratories around the world, where they are dissected atom by atom. They are teaching us about the stellar nucleosynthesis that forged the elements in our bodies, the condensation of the solar nebula, and the delivery of water to the inner planets. They are providing ground truth to our models of asteroid formation and evolution. On the other hand, we have the engineering triumph and the continuation of the voyage. The mission demonstrated that we can navigate to a small, tumbling rock, map it with unprecedented precision, and interact with its surface. It taught us that our assumptions about the physical properties of asteroids, like the cohesiveness of their surfaces, can be fundamentally wrong, forcing us to adapt and innovate in real time. The plastic ball pit, nature of Bennu's surface, has rewritten the textbooks on asteroid geophysics, informing how we might design future deflection missions should an asteroid ever threaten Earth. As we analyze the magnesium-sodium phosphate, the pre-solar grains, and the organic sludge returned from Bennu, we are effectively looking into a mirror. We are seeing the raw materials that, through a sequence of unlikely events on the surface of the early Earth, organized themselves into replicating structures, into cells, and eventually into the conscious observers who built a spacecraft to go back and find them. The story of Bennu is, in a very real sense, the prologue to the story of us. It is a narrative written in isotopes and minerals, preserved in the cold vacuum of space, and now, finally, deciphered by the persistence of human curiosity. The strange substance is not just a chemical oddity. It is a clue to the universality of the conditions that make life possible. And as OSIRIS-REx sails toward Apophis, the exploration continues, driven by the knowledge that the solar system still holds countless secrets waiting to be uncovered. The discovery of the water-soluble magnesium sodium phosphate was particularly serendipitous. Because the samples were kept in such strict isolation from Earth's atmosphere, the delicate structures of these phosphates were preserved. Had they been exposed to terrestrial humidity, they might have dissolved or altered before they could be identified. This underscores the vital importance of sample return missions. Remote spectroscopy can tell us a great deal. It can identify water hydration bands or the presence of clays, but it cannot identify specific salt crystals within a rock matrix with this level of certainty. It cannot sequence the chirality of amino acids to see if they match the left-handed bias of life on Earth. Only by bringing the material home can we apply the full weight of our analytical technology. Furthermore, the geological context of Bennu offers a cautionary tale for planetary defense. The realization that Bennu is a loosely bound rubble pile with a high porosity means that it would react differently to a kinetic impactor than a solid rock. If we were to try and deflect Bennu by slamming a spacecraft into it, the energy might be absorbed by the porous structure, dampening the effect, or worse, the asteroid might simply break apart into a shotgun blast of smaller fragments. Understanding the internal structure, the void space within the asteroid, is crucial. The data regarding the density and the gravity field measured by OSIRIS-REx provides the parameters needed to model these deflection scenarios accurately. The mission also highlighted the ubiquity of carbon. The samples are roughly 5% carbon by weight. This is a staggering amount for a rock. It confirms that C-type asteroids are distinct reservoirs of volatiles. In the grand dynamic of the solar system's history, the migration of the giant planets, Jupiter and Saturn, likely scattered these carbon-rich bodies from the outer solar system inward, raining them down upon the rocky inner planets. This late heavy bombardment, or perhaps earlier influxes, coated the sterile, cooling Earth with the carbon-rich mud that would become the biosphere. Bennu is a remnant of that delivery fleet. In the coming years, as the catalog of compounds found in the Bennu samples grows, we can expect further surprises. The gum-like compounds mentioned in early reports hint at complex polymerization processes occurring in the interstellar medium or on the parent body. The diversity of the organic inventory suggests that the chemistry of space is far richer than previously imagined. We are moving away from a view of space as a sterile void to one where the fundamental components of biology are manufactured in the dark clouds between stars and the interiors of frozen asteroids, waiting only for a warm, wet world to take root. The OSIRIS-REx mission serves as a bridge between the disciplines of astronomy, geology, and biology. It unites the study of the very large, the formation of solar systems, with the study of the very small, the isotopic ratios of microscopic grains. It reminds us that the Earth is not a closed system, but an open one constantly interacting with the debris of its cosmic neighborhood. The strange substances on Bennu, the ancient dust, the hydrated clays, are all pieces of a puzzle that, when fully assembled, will reveal the origins of our habitable world. The slow, meticulous work of analyzing these samples will continue for decades, ensuring that the legacy of this mission extends far beyond the lifespan of the spacecraft itself.